All right, you guys will be amazed at how much of the chattering it can pick up. So, when you watch this, from today, you can actually try to pick out some of the conversation that's still going on right now. And
get a blowhorn, just be like.
But that would make me part of the problem too. So. All right, let's go ahead and get started. All righty. Okay. Do you guys have any questions? No questions? Okay. Yep, go ahead. I just put it up today, so the due date is 1 week from today. So it's you guys have plenty of time to work on that one. Let's talk about the one that you guys turned in already that I graded last night, early this morning. The class as a whole did really well, and a few people forgot to customize LibreOffice or OpenOffice with their names. And if I cannot see the names, in the document, there will be no points. Okay, so only a few people got that, 0 point out of 5. And remember, these are 5 points out of maybe 600, and the 600 points is 20% of your final grade. So we are talking about a tiny little fraction of your actual final grade. It's not the point value that is important, it's getting the whole thing set up that is important. Okay, understanding what I expect, what type of file, and the format, and also the standard that I'm expecting that is important. Yes?
Doing the homework in the lab, when we log in with our name, does LibreOffice recognize that? Does it grab it and acknowledge that?
Well, you can check. If it does not, you can customize it at that time. And that's why I recommend you to use the portable version of LibreOffice. Okay. I think I went over that briefly, at least, the portable versions. So what you need to do is to go to portableapps.com and then go to Get Apps. And this is an Office app, so you have to look under, let's see. I thought I opened the door already. Can you check whether it's locked from the outside? Okay,
The speaker's quiet.
Okay. Okay, so what you want to do is to go get a LibreOffice portable. So go to this link here, and just download it. And for the most part, I think it's just a file that you can unzip onto an external hard drive or a thumb drive or SD card. And with this, once you customize it, it stays with you. Everywhere you plug it in and you start up the application, it retains the settings of yours. Okay? So this is a good way to go if you want to use the lab machines, and use the version that is installed in the lab. Then what you want to do is to make sure that you customize it every single time. It is okay.
When you close it.
Okay, so that means you have to push the door in and then turn it, because what happens is the door it's being pushed the one way or another. I guess I'm not going to test it. All right. So is that part okay? Does everybody understand what LibreOffice Portable is and why you might want to consider using it? Because once you install it on a cheap 8 gigabyte SD card, you can just take that 8 gigabyte SD card to any Windows machine and use it. You don't have to install it on any machine. Any questions? No questions? Now, what it takes up all the way. If you install just the let's see, what is the difference? This one is all languages. So even with a multilingual version, if you do a full installation, it will take up less than 1 gigabyte of storage. So it doesn't really take up that much storage. Okay. Do you guys have any questions back there? Any questions? Nope. Okay. Very good. I'm going to test it. I'll take my keys so that I don't get locked. I don't lock myself outside, and then you guys can say, "Well, I don't think we'll let Tag back into the classroom." So I'm going to take my keys with me, just in case.
We're going to be watching YouTube until 12 o'clock and then let you in. Oh, okay, works.
This guy.
Not a problem.
But it's not as good as you, Tech.
Turn and then pull.
Oh, that's how it works.
So you're not supposed to pull and turn?
Well, some people do the pull and then try to turn at the same time. You know, it doesn't work. It works with some doors, but not this one. I think the latch is a little sticky, so you have to turn all the way first and then pull.
That's special.
Yep.
So does that mean that we should just, the next person that tries to get in here and doesn't do that, should we just like leave him out there?
Yeah.
And figures it out himself.
We'll put a label on the door and just say, you know, emphasize the fact.
Side to give directions.
Still have instructions.
Instructions, yes. We'll
Still
give.
do it.
We'll write an algorithm.
You got the code, but you don't know how to open the door.
All right.
It happens.
Yes, it does. Okay, so is that it? Are there any questions about this? I can't really show you the scores. You know, I can turn on ranking. So when you look at your score, you can actually see your ranking as well. You know, how do you rank in this class? It will show a number like, you know, 23/50 or something like that. That means it is ranked 23 out of 50 students. The smaller the first number, the better, because that means you're ranking, you know, at a higher place in the class. Now remember, you know, the grading part is not based on ranking, so don't, you know, worry if you are like number 45 out of, you know, 50 when you already have a score of 90%, because, you know, maybe the whole class did really, really well, and the 90% is already ranked, you know, 40 out of 50. So that shouldn't let that, you know, don't let that worry you. Okay, any questions? No questions? Let's move on to the next homework assignment. I will describe it a little bit. This is stuff that you should know how to do already, because we have already talked about multi-branch conditional statement. So same thing with all the homework assignment. You have to download a file. So right-click and then save the file. I'll put it into a folder that I created for today. So let's go ahead and use this prompt here. Okay. And then I'll go ahead and put it inside this folder. You don't have to change the name of the document. There's no need to change it, because when you turn it in, you have already signed in Moodle under your name. So I know exactly who turned in what. There's no need to customize the file name. If you want to customize, it doesn't, you know, really bother me. Well, 2 people turned it in already. Excellent. Doesn't mean that they're correct. You know, it's just that 2 people turn in a file of some kind for this homework assignment. All right. So once you download the file, you can open it, and this is the content of the file. The algorithm looks like this. It is something that we talked about. You know, we talked about something very similar to this, not exactly the same. I cannot remember. Maybe it was exactly the same that we talked about last week. I cannot remember. I don't think they're exactly the same, but they're close. So this is the algorithm. Based on the comparison between x and y, I will set different values into the variable z. And you have 3 test cases in this case. In other words, you have to produce 3 traces as a result. The first one is in sheet 2 of the spreadsheet. So basically, I already pre-formatted all the columns for you. 1 column for comments, 1 for line number, 1 for x, 1 for y, and 1 for z. I even make all the preconditions for you, because without knowing the initial value of x and y, there's no way you can actually compare and see which way the program is going to go. So that's why I have to make sure x and y have initial values. Z does not have any initial value, because one of the branches will give z a value in the end. So your job is to trace the algorithm using all the conventions that we did last Thursday. Okay? Do you guys remember what we talked about last Thursday? Yes? If the answer is no, don't worry. You can go to YouTube and watch the lecture again. Okay, so there's sheet 3. sheet 3 and sheet 2 are about the same, except the initial values of x and y are different. And there's a fourth one, which also has a different combination of x and y. The 3 test cases cover all 3 possible cases, where x is less than y to begin with, x is greater than y to begin with, and x equals y to begin with. There should be no fourth cases. That means at least one of the branches of the algorithm is a dead branch, because none of the 3 test cases will touch it. Are we doing okay so far? Now, you don't have to figure out or report which branch is a dead branch, but it should be obvious by the time you get to sheet 3, it should be obvious which branch is a dead branch in the algorithm. Any questions about this? Yes, sir.
I'm sorry, can you just show us one more time how to open another window so you can look at the same file?
Absolutely.
You'll never get there.
Okay, I would open up, in the algorithm page first, and then you go to Window, go to New Window. And once you open a new window, it creates a new, it looks like a new application, but it's actually a different window on the same document. So each one, it's independent now. You can use, you can look at a different sheet, or even within the same sheet, each window can look at a different portion of the same sheet. Is that good?
Yeah.
All right, excellent, sure. Okay, any other questions about this homework assignment? You have a whole week to work on this. So that's 168 hours minus 15 minutes. I consider that quite a bit of time to work on this one. Now the algorithm looks a little bit lengthy, but the traces will be actually much shorter, because remember, in a multi-branch conditional statement, you only take one branch at the most. So that means, if your algorithm is tracking line 2 and then line 4 and then line 6, something is not right. Only one of the assignments should execute. If you're executing more than one assignment statement, something is wrong with the trace. Okay, so that's your current homework assignment, and we'll move on and talk about a new topic at this point. So the next topic we want to talk about are loops, and this is where the notes is. And what I'll do is I'm going to talk about this, but not necessarily using the notes, because I really don't like reading from my notes. Okay, at this point, what type of tools do we have for specifying an algorithm, a method of doing things? We have the most basic stuff, which are variables and assignment statements. Now those two will give us the ability to store information, because that's what variables are for. You can store values into the variables and change those values along the line when you execute a program. But to change the value of a variable, you need an assignment statement. And we know that assignment statements will have to follow the sequence, one and then the next one, and so on and so forth. Not very helpful, they're useful, but not entirely useful. The next thing we talked about are conditional statements. Conditional statements buy you one additional capability, which is very important in programming. It gives you the ability to evaluate a condition. Based on the evaluation of the condition, your program can now choose one of several paths. Most of the time, you can just look at it as one of 2 paths, because the question always is answered with an answer of true or false. If it is true, you go one way. If it is false, you go the other way. But that gives your program the ability to choose, which is a very, very important concept. Okay? But at this point, when you look at the program as a picture, we are always going in from the north, from above, and in between it can branch and you can do a lot of crazy stuff. But eventually, in the end, it is always going in one direction. It's always from top to bottom. You cannot say, I want to do this again. We don't have the mechanism to do something again. So why do you want to be able to do something again? Repetition or iterative stuff. Why do you want to be able to specify the logic to do something again? Tell me something that you did today that is repetitive. But go ahead, ask the question first.
Before you made that statement, I was going to say if something's not met, if the condition's not met, you go back and repeat it again until that condition is met, and then it just shoots out the bottom.
Exactly. So what did you do today that requires the logic of a loop? You have to repeat doing something until a condition is met.
Checking your clock, your watch. this until.
That's a little complicated, but that's something a lot easier.
Going to class.
Going to class, how about finding a parking space in the parking lot? That's a very repetitive process, isn't it? Okay, especially when the lot is entirely full and you cannot find a single empty spot, then you have to one big run round, go through all the aisles, you know, okay, no parking space, and then you have to do it all over again. When do you stop? You either find a parking space or the class has ended already. Okay, right? Or you run out of gas.
Very possible.
Okay, but that tells you something. Okay, when you have something that is repetitive, it is also important to remember, but how do I get out of this? How do I stop the repetition? Okay, so we have just talked about, you know, repetition loops in general. Are there any questions about repetition in real life, just at like parking, or you're doing your dishes? Okay, when you're doing dishes, washing dishes, it's repetitive. Pick up a dirty dish, you know, wash it, put it on a pile, pick up another dirty dish, you know, do it, and then do it this way. So it's repetitive. Are there any questions about the general idea of something that is repetitive? In English, what gives you the clue that a task may be repetitive? What words do we use that will make that suggestion?
Rinse and repeat. Rinse and repeat.
Okay.
Until.
Again, until, what else? While. Anything else? As long as. Okay. So there are a lot of words in English, you know, and I'm pretty sure it's the same with other, you know, natural languages that would give you the idea of, yes, this is something that has to be done again and again. And in most languages, you can also specify when can you stop doing it, when can you stop the repetition. So what we'll do is we'll go through an example, and I'll show you some pictures, you know, of what a loop looks like. I'm changing the order of the presentation. I'm going to start with a while loop this time. Okay, this is the first time I teach this class that I start with a while loop. In other words, I start with topic number 5 instead of topic number 3, because those one is a pre-checking, one is a post-checking loop. So I start with while loop here, and we'll go ahead and take a look at the picture. Okay, so this is about eating. Okay. And we are making the assumption that you're eating at a buffet place. In other words, you cannot say, I ran out of money, I cannot buy any more food. Someone already paid for your ticket at the buffet, so you can basically you can eat until you are full. All right, this is the logic. So we'll go ahead and take a look at this picture and say, well, how exactly is that logic? This looks like a picture from a biology class, doesn't it? Except I don't think in human beings there are loops in our digestive tracts. In some other animals, maybe, but certainly not in human beings. Cows.
Yeah.
Okay. So what we do is we have an entry point, which is this open end here, and we have one single exit point, which is this point here. So upon the entry here, it looks like we can go this way, but that's not true, because if you look at the arrows, that's a one-way street. Okay. So we can't really go to the left-hand side using this route here because that's a one-way street. So you have no choice but to continue. But if you continue at about this point here, you have to make a choice because there are two ways to proceed. The first way to proceed is right down, just like this, and then you go to a little bubble that says take a bite. And the other way to proceed is to proceed on the right-hand side, and this path will go all the way to the end, and you'll be out of the loop. Are we doing okay so far with following the arrows? Okay. But every time you have two ways of proceeding, there has to be a question that you have to answer so that you can determine which way you want to go. In this case, the question that we are asking is that person still hungry, or is that person not full at this point? If it is true that that person is not feeling full yet, then you will follow the path of true and then take another bite. What do we do after taking a bite? This is the main difference between a conditional statement and the loop. You have to go back up. Okay. So after you take a bite, you follow this path here. It goes all the way around. It quote unquote loops back to the beginning. And the exit point of this loop is right before the decision point. In other words, right after you take a byte, it will take you all the way back to the beginning. You ask the question, and you answer the question, and then you can decide which way to go again. Are we doing okay so far with this logic? So as long as that person is not feeling full yet, then you will basically be going through this loop again and again and again. But for every iteration, for every time you go through this loop, you have the chance of asking the question, answering the question, and then decide whether you want to exit at that point or not. Are we doing okay so far with this picture? So you can see from the picture, this is not nearly the same as a conditional statement. The only part that resembles a conditional statement is right here, right at this junction here, where you have a choice to go either down, when the answer is true, or to go right when the answer is false. That's the only part that resembles a conditional statement. Yes, sir?
Is it possible for the true and false to be opposite?
Reversed? In this class, no. In this class, we always, we always label the path going into the loop, true, and we always label the path getting out of the loop false. Okay, so in this class, this is the way, it is specified. In an actual programming language, in C, it's the same way. Okay, C can only deal with, a picture that looks like this. In some other languages, such as Perl, there's a different mechanism, and you can actually flip the labeling of the two paths. Did I answer the question? Okay. All right. So if this is the picture, this represents the logic that I want to express. What does it look like in pseudocode? Oh, that brings us up a little bit, and this is the pseudocode that represents that logic. So if you want to read it out, it actually reads kind of like English. While one is not full, do take a bite and while. Okay, the logic, the question, the condition is here. One is not full. Okay, the action that you want to perform is over here, and while is nothing more than a marker to mark the end of the loop. It doesn't serve any purpose other than that. Are we doing okay so far with the logic, the picture itself, and also the text representation in pseudocode? Yes? The indentation is important because we want to know what is the action that you want to perform inside the loop. We'll talk about that, the indentation part in just a little bit. Any other questions about this logic? Let's go ahead and actually write some algorithms using numbers and variables and see whether we can actually trace those algorithms. So let's go ahead and use our favorite spreadsheet program. And we'll say while x is less than k, do x gets x plus 1, and while, and that's my entire program. Now, when you look at this code, you know that I have to give you the initial values of x and k, because otherwise there's no way to perform the first comparison. Okay. So we'll go ahead and mark it like this. And I'll just give you two test cases in this case. And I'll save the document first, just in case I forget to do it later. I'll just call this one the while loop because it's a very, very simple while loop. Okay, so we need one column for comments because once again we have a condition to evaluate. Every time your program has conditions to evaluate and it determines which way to go, you have to have a column called comments so that you can tell me why the program is going one way or the other way. We have line number. And in this case, we have two variables. One is x and one is k. K, for the most part, is a constant in this case because you can see that no part in the program actually changes the value of k. So the value of k stays exactly the same throughout the execution of the program. X, on the other hand, may get changed. Now, I only said may because there's a case, it is possible that x does not get changed at all when you execute this algorithm. Well, we'll go for the easy one first. x has a value of k has a value of 3 to begin with, and x has a value of 0 to begin with. And this is my precondition. In other words, don't ask me why x and k had these values to begin with. It's just the way you are given. It is given. All right. Any questions at this point before we trace line 1? No questions? Okay. So we get to line 1, and on line 1, immediately we have to decide which way to go. Because what is line 1 in this case? Now let me switch back to the picture. Line 1 represents this point here. We are right at this junction. We have to answer the question in order to decide which way we want to go. All right. So we have to answer the question. X is less than k. Is it true or is it false? True. It is true. Very good. So according to the picture that I just show you, if the answer to the question is true, do we go down or do we go to the right? We go down. We go into the action. The action in this case is line 2. So we now continue the execution on line 2. Line 2 is going to evaluate the right-hand side. X has a value of 0 right now. 0 plus 1 is 1. The right-hand side has a value of 1, so we have to store that onto the left-hand side. The left-hand side turns out to be x as well, so x is now updated to a value of 1. This is boring stuff because we talked about this, 2 weeks ago, just about. And then what do? We go back to line 1. We do not trace line 3. Because line 3 serves no purpose when you're tracing the algorithm. It's only there to indicate the end of the loop. It has no other purpose. So we have to remember to go back to line 1, and this is the main difference, again, between a loop like this and a conditional statement. A conditional statement does not go back to the beginning, but a loop does. Well, now that we're back to line 1, we're going to evaluate the condition again. So every time you go back to the beginning, you have to re-evaluate the condition. X has a value of 1. 1 is less than 3 is true. True. Okay. So the rest of the algorithm gets a little bit boring, just like that. What about this in this case? It's still true because X has a value of 2. 2 is less than 3 is true. So now we go to line 2 again. Line 2 is now updating the value of x to 3. We go back to line 1. 3 is less than 3 is false. And then where do we go? Exactly, we go to post right away. We do not go to line 3. Once again, we do not trace line 3. Are we doing okay so far with this particular test case? It's good? Okay. So let me save the document first, and then we'll move on to the next test case. I'm just being a little lazy here and do some copy and paste. Now in this case, I'm going to give you a tricky case. Okay, what if x starts with a value of, say, 5? Okay, suppose. So, well, if I gave you something like this for the exam, you should thank me because it is an easy one to deal with. Well, not yet. Okay, you still have to start with line 1. Okay, so on line 1, you still have to evaluate the condition. X is less than k is false to begin with, and then you go all the way to post. You're done. Okay, so is everybody getting the concept of a while loop? In this class, yes, go ahead.
To me, in my head, it seems like the while loop is the same as the if-then-else statement.
It is not. What makes you think they're the same?
Well, it seems like it's a counter. If you're trying to count to 10 and you add 1 each time, if the condition is not met, it goes back again. You say if x is less than k.
But there's no if in the while loop. A conditional statement, which is an if statement, does not go back. It does not give you a mechanism to go back. Whereas a loop does go back.
Well, in an if statement too, you have 2 branches you can go down. You can go down and have two different actions.
But both ways are down.
Yeah.
If you want to
it's not the same way as that.
But this one does not. Well, one way going down will eventually go back up again. That's the different part of a loop. Yes.
Maybe the main difference is the code is way shorter.
The code.
The code is a lot
lot shorter on that one. It's 3 lines.
It's 3 lines, but you can write a conditional statement that's exactly 3 line too, which is if x is less than y, then x gets x plus 1, and if. So that's 3 lines too, and it will do almost exactly the same thing. In some cases they're exactly the same, but in other cases they're different. Okay? Yep.
So syntactically, the difference between while and if is that while implies that this may happen again.
While sets if you perform the action on line 2, you have no choice but to go back to line 1 and then reevaluate the condition. Whereas with a conditional statement, after you're done with line 2, if this were an if statement, after the line 2 you get out of the statement. You know, the condition may still be true, but I don't care. You have to get out. Okay. Any other questions? No? Okay. So the best way to kind of envision, you know, the difference between a conditional statement or a whole bunch of conditional statements versus a loop is like this. A conditional statement is like a waterfall. Okay, if you look at a whole bunch of conditional statements, it's like a big waterfall. You know, water goes, you know, comes from the top. When it hits the rocks and whatnot, it may break apart. But in which direction do they go? It's always down. Okay. In other words, if you look at the path of the water, it can break up and then break up some more and it breaks up even some more. But in the end, they all have to go down. In that analogy, a loop is more like a fish pond where you have a pump to recirculate the water. So the water, you might have an artificial waterfall, but the water gets pumped up back to the waterfall and it goes back down again, it goes up again, and it goes down again. There was a hand. Yep.
Is there, in the conditional statement, if then else, is there something that says if x is less than k, execute the formula, else repeat?
No. No.
That's an error, okay.
Well, I lied, but you should not know that.
That's what I was in my head. I was thinking the two would loop.
Okay. Well, I should mention this, just so that I get it out and you guys know how I see it. Okay. There is a construct in most programming languages called goto, G-O-T-O, goto. Okay. And in programming, that's a taboo word. Okay. If you say goto in classes, in a programming class, the teacher will toss you out of the classroom.
Why?
Because it's a big taboo to use gotos. When a program uses gotos, it becomes very difficult to debug because your program is quote unquote no longer structured.
Oh.
I can't really get into much of that because the next module talks about what is structured programming. So we are kind of way ahead of that curve. But there is a construct called goto to do what you think you should be able to do. And the answer is yes, you can, using gotos, use a conditional statement to implement a loop, but it's a very, very, very bad idea. Okay? It's kind of like, when you load a gun or something, you can load a gun with a muzzle pointing to yourself. It's just a bad idea. Very, very bad idea.
Try to keep that in mind. Try to keep that in mind.
Yeah.
So do go-tos use the line number, or do they
You can define labels
Okay.
anywhere in the program, and the goto will get to that label. That makes it very, very bad. I should also mention, the term, it's called spaghetti code. Okay. Spaghetti code refers to programs that are specified where the logic is specified in such a convoluted way that if you try to follow the path of execution, it's like following, is it called a strand of spaghetti? How do you call one piece of spaghetti in a bowl? One strand, one piece.
Close enough.
Close enough.
Let's do a strand.
Okay. So it's just like trying to track it down in a bowl. It's really hard to do because it goes in and out and intertwines with other spaghetti, and that's called spaghetti code. If you want someone to curse you 20 years after you leave a company, that's the kind of code that you write.
That's the way you're trying to make yourself irreplaceable.
Yes.
So there's no good reason to use that at all?
With gotos?
Yeah.
Some people argue that there are cases where it is actually legit to use gotos. I would argue that you should never ever use gotos.
Okay.
Yeah. There are other mechanisms to do what we call exception handling. In other words, there's no way to proceed at this point anymore. We need to get out. Okay, that's basically when people say, well, it's okay to use goTos here, but I would argue that that's not the case. There are other mechanisms that you can use that are much better.
Okay.
Okay. I forgot what I was about to say a few seconds ago. Unfortunately, the recorder does not record what I'm going through in my mind. Otherwise, I could just replay that. Yeah, goTos are bad until you get to assembly language programming, cisp300. You know, and only I teach that class here. So when you take cisp300, you know, you have to take it from me. Yeah, you don't have a choice there. Okay, but in that class, it's all goTos, because in assembly language programming, there's no such thing as if, there's no such thing as while, there's no such thing as a conditional statement or a loop. You have to build everything from the ground up using tiny little programming concepts. This class uses, you know, fairly high-level concepts, so it is kind of equivalent to building, you know, something using Lego pieces. Okay, so there are pre-formed Lego pieces that are flat, that are long, that interlocks with other pieces in certain ways. So you don't have to worry too much about, you know, stuff. Okay, you know, you can focus on the design of the object. Assembly language programming is almost the same as building stuff out of sand, grains of sand, to be more specific. Okay, so here's super glue and here's a bag of sand. I want you to make blah 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 blah. That's assembly language programming. In other words, the building blocks have almost no structures whatsoever to themselves. You have to impose the structures, you know, using that method. Okay, and in those classes, you know, in the end, you know, my students will be building like, you know, big sand castles or sand trucks that can actually run, you know, stuff like that. The concept of that class, the most important part of that class in assembly language programming is when you build the smallest pieces, you use structure programming principles that we will use in this class. So the whole thing is not the language or the tool, it's how you create the algorithm, how you think and how you create the algorithm. But that's kind of way ahead of you because you have to get past cisp360 before you get to assembly language programming. This is a good time for you because, you know, in the spring semester, it's only in the spring semester that we offer cisp310. So if you pass this class with a C or better, then you can take cisp360 in the fall, and then next spring, you can take cisp310. So that would be like a perfect schedule for you. Alrighty. Okay, so let's get this part done. Now we have a problem. Some logic does not really fit into this template. In other words, asking the question first is not always the best idea. I'll give you an example. My example is something like this. Let me see how I should put that. Let's use Office. Okay. I don't think I can trace this one. What about something like this? While zip code is invalid, do ask user for a zip code and file. I'll just describe what I want to do here, and then you can tell me why this is a bad idea. So this is a logic that I want to put into an interactive program, which at some point has to ask an end user for a zip code. Okay? Why is this logic faulty? Why is
You don't have a zip code yet.
the first time? Okay, the first time when you get to, I'll give it line numbers so that we can refer to the actual lines. Remember, with a while loop, you ask the question first. You do not perform the action first. In other words, if I were to execute this code, the first thing I do is to say, is the zip code valid or not? But that's before I even ask the user. I don't have a zip code to validate at that point. So that's why, you know, this kind of loop, most of the time it works, but for certain cases, you don't have anything to check when you execute line 1. And that's why a pre-checking loop is not always the best logic. I would say around 10% of the time, when you have to use a loop, you cannot use a while loop. The other 90%, you can use a while loop. You can ask the question first. Are we doing okay? Why this is not the best logic to specify? Because by the time we evaluate the condition the first time, the variable is not set yet. Okay, we have not asked the user to say anything yet. So with that in mind, let's go ahead and look at the solution. How do we fix that problem? The way we fix that problem is to use what we call a repeat loop. And let me show you the picture of a repeat loop first, just so that we can so we know the logic of it. This is the picture of a repeat loop. You can see it is still a loop. How do we know this is a loop? You can see this path here going back to the beginning. But the difference between this one and the previous one is obvious. With this one, you come in from the north, okay? You come in through this entry point, and you go straight down. There's no decision to make, and then you take a byte or perform the action regardless. In other words, you always perform the action at least once. You don't have a choice the first time. After you perform the action, then you get to this junction here. You get to this branch or junction. At that point, you can say, well, let me ask a question, and then depending on the answer of the question, maybe I want to go this way, or maybe I want to go the other way. If the answer to this question, 1 is full, is true, then you actually get out of the loop. If the answer to the question is false, only at that time you follow the path all the way back to the beginning, and then you perform the action again. Are we doing okay understanding the basic logic of this kind of loop compared to the one before? Yep.
Okay, I don't know if it has any real significance, but is there a reason why the picture kind of flipped around? Or
Sorry?
is there a reason why the picture kind of flipped around, or is it just,
The picture is?
you know how you have the little diagram?
Mm-hmm.
You have the other way earlier.
The other way?
The loop was on the other side.
Yeah. I don't know.
Oh, no particular reason.
Well, because this one, if it's false, because false is always to the right and true is always to the left. And so on the while, it's always true, so you always go left, but this one it's false, so you go right.
Yep. But since it's a picture, I could have labeled it the other way too. Yep.
Is there a reason you have true leaving this time when, like, and having false be the repeating part, when last time you had false be the leaving and then true?
Well, the only reason for that is because this is what we call a repeat loop. So when you use a repeat loop, you can say that in English too. Repeat doing something, something, something until something, right? So, okay, let me just use a concrete example. This is something I tell my kids. Okay, repeat, do your homework assignment until it is done. Okay, so let's think about until it is done. When do we get out? Do we get out of the loop when the homework assignment is done, or when it is not done? Until says, basically what we use after the word until is an exit condition. Does it make sense? That condition specifies when can we stop the repetition. Is that how you understand the use of the word until in English? Yes? So that's why the picture looks like the picture that I just drew. When the condition is true, you get out of the loop. Now, when we use the word while in programming, you can kind of see it as long as. Okay, while is equivalent to as long as in normal speak. So that way you can actually you can compare programming concepts with just normal usage of the language. Yep.
Do the while and repeat loops, do those replace the for next for x equals 1 to 100 next to x or something? Is that the newer way?
No, it's not a newer way. It's just a more general way. The for next that you're talking about, which exists in C, Visual Basic and most other basic implementations, can be implemented with just while loop with a while loop in that case. So it's a shorthand. The for loop is a shorthand of a more complicated while loop. So you can initialize, you can specify the range of the numbers, and in some cases you can even specify the step of the number. Like you're increasing every 3 or 5 or whatever. So you can specify the step also in a for loop. It's a shorthand. It makes the program just easier to read. Okay. All right. Well, let's go through a few examples with a repeat until loop, and then we'll wrap this up, and then we'll move on to the next topic. right. So once we understand the concept of repeat until, the best way to specify the logic of validating a zip code is to do something like this. You say repeat, ask user for a zip code until zip code is valid. That makes a whole lot more sense than the logic before, doesn't it? Because in the second case, we always ask the question first, and then we say, well, is that zip code valid? That's the difference. Now, let me just give you the naming of these loops in this class. Some people just call this a while loop, and this is a repeat loop. That's okay too, but it is not really the best way to specify these loops, because in certain languages, including Visual Basic, there are variants that will make, when you say a while loop, it is not exactly clear which type of while loop you're talking about. When you say it's a repeat loop, it's not clear exactly which repeat loop you're talking about. So the best way to describe these is, this is what I call a pre-checking loop. Can anyone tell me why I would call this one a pre-checking loop?
Because it checks the condition before the action's done.
Exactly, we check the condition before the action is done. Therefore, it's called a pre-checking loop. And can anyone kind of guess how I would call this one?
Post-checking.
A post-checking one, exactly, because we check the condition after we perform the action. Is that okay so far? So in this class, a lot of times I would use those terms to refer to these two different types of loops. 90% of the time, this is going to work out just fine. About 10% of the time, you need something like this. Are there any questions so far before we go ahead and trace a repeat until loop? No questions? All right. Let's go ahead and trace, maybe one or two of those repeat until loops or post-checking loops. And once again, I'll just use one single code and then give you different preconditions so that we can see how it works out. Okay, x gets x plus 1 is inside until x is less than k. Well, let's make it like this. This one is tricky. So I'll give you a few tricky ones like this. The logic itself is not that tricky. It's the conditions that I give you that will make it tricky. Now, if you look at this code here, this is the action, right? When you come into this code, you have no choice but to execute line 2 once first. And then you go to line 3, you evaluate the condition, and then you can decide whether to go back to line 2 or go to post to end the entire loop. That's the meaning of this loop. But by making changes to x and k, I can create some pretty tricky cases. If you don't find it tricky, then you're doing pretty good in this class. All right, so we'll specify a precondition, and let's go ahead and do this. Oops. So we can see the algorithm and also the trace at the same time. So we'll start with something really simple, 0 and 3, just like kind of like the other one. This is similar to the other loop, the for loop. I mean the pre-checking loop. And we'll go ahead and save the file first. All right. So given this is my precondition, I don't track line 1 because line 1 serves no purpose other than indicating the beginning of the post-checking loop. So that's why we don't trace line 1, because if you were to write down line 1 here, there would be no meaning to it. There's nothing to evaluate, so the comments column would be empty, and it doesn't make any changes to the variables either, so that it really serves no purpose, and we don't trace it. So we start with line 2 in this case. Line 2 is pretty easy to figure out. It just adds 1 to x. We are done, right? X was 0. Now it is 1. We go to line 3. We know how to evaluate this sort of thing. X equals k is false. Okay. So according to the picture that we saw earlier, when the condition is false with a post-checking loop like this, we have to go back to the beginning. Because the condition we are specifying here, which is x equals k, is called the exit condition. When it is true, we get out of the loop. So when it is false, we have to stay in the loop. All right? If we stay in the loop, we go back to line 2. Line 2 adds 1 to x again. becomes 2, we go back to line 3, 2 equals 3 is false, we go back to line 2, x is incremented again to 3, we go back to line 3, 3 equals 3 is true, and we get out of the loop, we get to post. Fairly simple stuff. It looks almost similar to the one that we talked about earlier. Okay. Any questions about this one? Yes?
If we're doing for homework something like this, is it absolutely mandatory that we, in the comments line, we write like x is incremented or x is initialized? Is that like
This is what I would expect. You know, the comments is only there to tell me the result of the expression in a condition. So you don't have to say it is initialized here. If you want to add additional information to comments, that's fine with me. It's not a problem. But this is the minimum that I'm expecting. Okay. So this one is not too tricky. I mean, this is really just fine. Okay. Let's take a look at the next one. So I'll work on another test case here. The next test case is to specify 2 for x, and then we'll see what happens. Really shouldn't be too difficult. We start with line 2 again. Line 2 adds 1 to x. X becomes 3. We go to line 3. X equals k is true. We get out of the loop, get to post. We are done. In fact, this one is so much easier than the previous one, right? Now we'll take a look at another test case. In the next test case, we'll just say, well, the previous test case is simple, but I think we can make it simpler by making x the same as k to begin with, right? I mean, you know, after all, we get out of the loop when x equals k, so this one should be even simpler than the loop before.
It's going to be an endless loop.
This is going to be, yeah, this is going to be, so, well, let's find out what it does. Now remember, when you trace an algorithm, it's not based on what you think the algorithm is specifying. You have to specify the actual code in the algorithm, okay? So we have to start with line 2. So right away, it is deviating from what a non-programming person would do when that person is looking at this code. A non-programming person will say, well, but you said until x equals k, but since x equals k already, we don't have to do anything. But when you're tracing an algorithm, you don't have that option. You have to see the program as the computer will see the program. And the computer starts with line 2. This is a post-checking loop, which means you always perform the action at least once. So here we perform the action, 3 becomes 4, and then you go back to line 3. You go to line 3, x equals k, guess what? It's false. All right. Now, don't we have a problem now? Because we go back to line 2, 4 becomes 5. We go back to line 3. That's false. We go back to line 2, line 6. 5 becomes 6 because we're just adding 1 to it. We go back to line 3 again. X equals k is false. And I can keep doing this forever and ever, and it will never end. Right?
Well, it would end eventually when you run out of room on your hard drive.
Well, but it won't run out of room on the hard drive. This is not going to run out of room on the hard drive because it's not actually saving anything in memory. Now, when we do a trace, yes, the trace gets longer and longer. But remember, we only do a trace so that we can see how a variable changes over time. But when this algorithm actually executes, as by itself without a trace, it doesn't consume memory as the loop goes on. It just consumes processing power. Question?
Isn't there going to be a point where the integer overruns its bounds?
Exactly. Now that is something that is worth mentioning in this class, but it will take some real understanding of how numbers are represented. But I'll go over that too. Yep.
So when a logical error like this happens, how do you break the loop?
That kind of relates to his question or relates to his point. Okay. All right. First of all, if x is a true integer, as in a math class, okay, then this will never end. What is the maximum integer? There is no such thing. Okay, there's no such thing as a maximum integer, because if you say that x is the maximum integer, then it will ask you, but what is x plus 1? It's an integer and it's bigger than x. Don't. right? So there's no such thing as the maximum integer because it is infinite. Okay, if you give me a maximum integer, I can always ask you, what is x plus 1. So from that perspective, this will never ever end because the value will just keep going higher and higher, and none of those values will equal to 3 anymore. We passed that chance to get out of the loop, right from the beginning. Okay, but when you actually write a program like this, the program does exit. It will stop. The loop it will take a while, but it will stop in the end. And you will ask, but why? I mean, mathematicians will say that this is impossible. But in programming, it is possible. And that's because of the way we represent numbers. Okay? Now, how do we represent numbers?
Binary code.
In binary code, well, it has to be a limited number of digits. Okay? Just like when you fill in forms, when you have your calculators and whatnot, there's a certain number of digits that you can use to represent a number. Okay? Now go ahead.
So basically you say that the computer ran out of number to do the loop?
The computer
ran out of number, like they cannot go any higher.
In a certain way of looking at it, yes, it is running out of numbers, and I will show you why. Okay, we'll just use base 10 for the time being. Okay, let's just say the computer internally uses, let's say, 5 digits to represent numbers, integers. Okay, so you have like 5 digits, 1, 2, 3, 4, 5. Okay, 5 digits to represent numbers. We start with 0. Let's only talk about non-negative numbers. We start with 0. Then we have 1, 2, 3, 4, 5, and so on. You keep adding numbers. You keep adding 1 to x, but eventually it will become 9, 9, 9, 9, 9. But since you only have 5 digits to represent a number, when you add 1 to this value, 99999, as a base 10 number, what happens to it? Well, there are 2 ways to go. One way is the program will quote-unquote crash. It will create an exception and say this number cannot store the sum of this value plus 1 anymore, and the program will just get out and say, well, we ran out of numbers to represent because we only have so many digits to begin with. That's one way that can happen. But since most of you are moving on to cisp300, I have to tell you what a C program will behave. A C program would look at this thing and say, oh, you want to add 1 to it? It becomes this number. Well, I look at this number and go but since I only have 5 digits to play with, I'll just take the first or the least significant 5 digits. And it became 0 again. That's how a C program will behave. Okay. Now, obviously, I'm changing the base because inside the computer, it's all based on base 2 and not base 10. But it's the same concept. When you run out of values because you have already run up to the number of digits allocated to represent integers, it goes all the way back to the beginning. It wraps around. Okay? So from that sense, this program will exit because at some point it wraps around to 0, 0, 0, 0, 0, which is representing 0. Then the next one is 1, the next one is 2, the next one is, guess what? 3, and then the program will exit. It will exit just for the wrong reasons. Okay? So are we kind of getting an idea of why conceptually this should never get out, but in practice it does get out? Yep.
So in non-C programs where it goes to 9999 and it just stops, what happens then?
I believe in Visual Basic it will stop, and then a little window will pop up on the screen and say your integer is running out of values, or the result of an expression cannot be stored back into the variable. You get a message, and it'll give you even a line number, so it's easier to debug that program. From that perspective, a VB program doing something like this is far more friendly to debug compared to C. Because C will just silently do this wraparound thing, and the program will exit, except it takes longer than it should. But you may not notice that it's taking longer than it should, and that's bad. Yep.
So from a user perspective, the answer will pop out the same, and they won't know the difference that there's an error in debugging in the code unless you debugged it.
In a way, it is what you just said. You know, the program does exit when x equals k, but in a way, it is also incorrect because if you have anything in between line 1 and line 2, all that stuff is going to be performed a lot more times than it is supposed to be. Do you understand what I'm saying? Because this loop doesn't really do anything, right? I mean, if I want x to be the same as k, I could have just said x gets the value of k, and I'm done with it. I don't need a loop to do it. So when you see a loop like this, typically you have a lot of code between line 1 and line 2. All that code is going to be performed close to 10,000 times, in this case, 100,000 times before it's done. But if your intent is really just to do it up to 3 times and is doing that more than close to 100,000 times, your program is going to do something wrong, probably.
The intent of this simplistic program, it's okay, but in the overall scheme of the program itself, where we have lots of other stuff going on, it would be obvious.
It depends on the intent of the program. And that's something that we have not talked about in this class, because we have only talked about the behavior of the pseudocode. So if you were to just follow the code line by line, this is what it would do. But we never really talked about what this code is supposed to do to begin with. So there's no comparison to call it wrong or right. There was another hand. No? Okay. All right. Well, since we are talking about number representation, let's go ahead and do a little digression and talk about base 2 conversion, because inside the computer, it's all base 2 or binary. Okay, bi means 2, so binary means base 2. What base do we use on a daily basis?
Base 10.
We use base 10.
Base 12, base 60 for time.
For time, we have base 12, base 60, which is a combination of it's a composite number. When you specify tool sizes, the SAE unit actually uses base 16. Because when you specify a tool, you can get a 1/2 inch range, you can get a 3/16 inch range. When you specify drill sizes, you can get 5 30-second, or some 5 30-second drill size. Those are base 2. Guess what? They're all base 2. All right. So we'll go ahead and just digress a little bit and talk about base 2. How many people already know about base conversion and feel totally comfortable with base conversion? Okay, there are a few. How many people think that, well, this stuff is just too hard, I can't do it? Certainly cannot be explained in, 10 minutes. So I will prove to you that not only do you already know base conversion, you know something that's far more difficult than base conversion. Okay? So here it goes. Not sure what tool I should use to demonstrate this. I'll just go ahead and use a free-form text editor like this one. All right. Let's think about money, okay? How many of you feel that you feel comfortable to work for McDonald's as a clerk? You know how to make changes, how to do the changes thing. Okay. How many people? I'll just reverse the question. How many people do not feel comfortable if I have to make a change of $6.32? I probably will end up giving that person 632 pennies. Nobody. So you guys know how to use like one $5 bill, one $1 bill, 2 dimes, and 3 pennies, right? Okay. Speed is not a problem. I'm just asking, do you know how to do it? Everybody feels comfortable? Okay, very good. You know base conversion already. Okay. Let's think about this. All right. View as dollars, coins, all right, let's see whether there's any type of regularity in this whole thing. We start with a base unit of 1 penny. In other words, when we count these things, it's all based on number of pennies. We start with 1 penny. The next unit up is what? A nickel, which is 5 pennies. The next one up is 10, which is a dime. And then we have a quarter, 25 pennies. And then we have $half, but let's not count $half because they are fairly uncommon. So we go to $1, which is 100 pennies. Then we go to, yes, we have $2 bills, but they're not common. So we move up to the $5, $10, $20, $50, $100 bills, I don't really know much about anything after $100 bills. I don't have that much cash. Okay, well, we can stop here. Is there any regularity from one number to the next? Is it always the same multiplier? No. In fact, it is very irregular. 1 to 5, and then 5 to 10 is times 2. 10 to 25 is times 2.5. 25 to 100 is times 4, and then we have times 5 again. And then we have times 2 again, times 2 again, times 2.5 again, times 2 again. There's no regularity whatsoever. And yet you know how to deal with it. Right? That is strange. I find that very strange that you told me earlier that you don't know anything, you think you cannot deal with base conversion. Now what base conversion is like this. So these are pennies. In base conversion, what we'll do is to start with $1. Okay, so in this new system, we'll have a $1 bill. Okay, so we'll have $1, and the next one up is $2. The next one up is 4, 8, 16, 32, 64, 128, and so on. In other words, the bills will all be powers of 2. Okay, 250, yeah, powers of 2. And then when we go to the fractional part, in other words, when we want to specify less than $1, we'll go with a $half, a $quarter, an $eighth, and if you feel like we have to specify anything smaller than that, we can go with a $16 too. Oops, there we go. All right. So this is the new money system compared to the old one. Well, yeah, it's kind of awkward, that we have to do with $16, $4, $8, $32, and $64. Very uncommon values. I mean, we don't do that in real life.
Wrenches.
We do it with wrenches. Okay, so let's see if we can figure out, how to make, how to specify a change using this new money system. Okay, let's see if we can do it. Let's start with something that's not too complicated. We'll start with I don't know. Let's start with $44. Okay. In other words, you have to give a customer a change of $44, and the values of the bills and the coins are as specified here. How would you go about doing it?
32,
Just
8, 4.
But kind of try to explain what is happening in your mind as you decide how much. Okay. Now, what I would do is to say, I start with the highest bill value. Should I give the customer back 128? No, 44 is less than the bill value, so I should not give a $128. 64? No, 64 is greater than 44. Oh, 32. 32 is less than or equal to 44. Okay? So that means if I want to give the customer a change of $44, I can give the customer $32 first, and I have $12 remaining. Does it make sense?
Yeah.
Okay, next, I look at the $12 remaining, and I say, well, let's see, the next value is 16. No, too much. 8 is good, right? So I can, with the rest of the $12 left, I can use $8 bills, and I will have a $4 bill remaining. I know it's already done, but let's just say that I don't know that. The next value down from 8 is a $4. So I can just say, oh, it's 4 plus 0. The 0 means there's nothing left. Okay, I have made, I have already given the customer the change that the customer needs. Is that making any sense? Well, but these are not binary numbers. These are just number the bills, the values of the bills that I have to give back to the customer. Well, but you can also see it in a different way. Okay, so if I want to write this again, I can say 44 equals to 32 plus 8 plus 4, right? In other words, I can express a value as a sum of powers of 2. 32 is 2 to the power of 5, 8 is 2 to the power of 3, 4 is 2 to the power of 2, right? What is so special about that? Well, let's see. I can rewrite it as this is 2 to the power of 5 plus 2 to the power of 3 plus 2 to the power of 2. Oops. There you go. So good. And I'll make this even dumber. So 1 times 2 to the power of 3 plus 1 times 2 to the power of 2, right? Because 1 times anything is just that value. But now I'll fill in the blanks. Because I can say this is 1 times 2 to the power of 5 plus 0 times 2 to the power of 4. Right? I can specify as many 0 terms as I want, and it won't change the actual sum. So I'm just going to fill in the gaps. 1 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 0 times 2 to the power of 0. Right? I'm just filling in the gaps. Can anyone guess the binary representation of the 44 value in decimal?
1, 0, 1, 1, 0, 0.
Exactly. I just pick out all the digits. 1 of 2 to the power of 5, 0 of 2 to the power of 4, 1 of 2 to the power of 3, 1 of 2 to the power of 2, 0, 2 to the power of 1, and 0, 2 to the power of 0. I'm done with base 2 conversion. And we spent about 7 minutes to explain base conversion. Don't you think we should change our monetary system to base 2?
No.
Zero.
Yes.
Well, but there are other advantages of base 2. We have 5 more minutes. I don't really feel like talking about the next slide, next module. So we'll just kind of focus on base conversion and stuff like that. In base 10, yeah, go ahead. Which one? Oh, that's just saying that this is a base 2 number instead of the default of base 10. Okay. And I'd say, at this point, if I were a politician running for, the presidential election stuff, my platform is going to be like this. I think we should change to base 2.
I like it.
And you know what?
We'll start.
Get the vote.
We'll start a new party called the Binary Party.
Yeah, you're either in it or not.
Yeah, 0 or 1, right?
Exactly.
All right.
Yeah.
Well, I think I can win the election because once people see what I'm going to tell you about, they will all go like, "Oh, yeah, we'll vote for the Binary Party." Okay. Here's the question. How many entries do you have to memorize when you were a kid in the multiplication table? Now, obviously, we are talking about a base 10 multiplication table. So let's go ahead and take a quick look at the base 10 multiplication table. All right, 0 to 9, 0 to 9. Okay, and we are so smart, we know that 0 times everything is 0. This row is not needed, this column is not needed, right? 1 is easy too, because 1 times everything is just that something itself, nothing to memorize. Easy. Okay, we just got rid of another row and another column. And then we realize there's the commutative rule in algebra. 2 times 3 is 3 times 2, so you only have to memorize half of the table and the other half is just symmetric. So we say, yes, the other half is not needed. How many entries do we have left? 8 times 8 divided by 2, which is 32 unique entries in the multiplication table. 32 items that you actually have to memorize. Let's think about base 2 multiplication. Now, when we talk about base 2, that means each digit can only be a 1 or a 0. There's no such thing as 2 as a digit in binary. There's no such thing as 3 as a digit in binary. Okay, zeros and ones is all that you have to deal with. What is 0 times 0 in base 2? In any base?
0.
It's always 0. 1 times 1 is always 1. 1 times 0 is always 0. 0 times 1 is always 0. That's my multiplication table. I think I can sell this to kids. I go back to 2nd grade or 3rd grade or whenever they learn the multiplication table. I think they will like me as a teacher. Don't you think?
Yes.
What about addition and subtraction? That's crazy stuff. Well, it's actually the same thing. You have to memorize that 2 minus 6 is 6 with a borrow. You have to memorize 3 minus 9 is 4 with a borrow. That's the stuff that you have memorized without even realizing that you have memorized it. Is that right?
Yes.
In other words, it's just like the multiplication table, except in the case of subtraction, it's not even symmetric. Okay? But what about binary subtraction? Well, okay, in binary subtraction, 1 minus 1 is always 0 regardless of the base. 0 minus 0 is always 0 regardless of the base. 1 minus 0 is always 1 regardless of the base. The only one that is tricky is what is 0 minus 1. 0 minus 1 is 1 with a borrow. Just like 0 minus 9 in base 10 is 1 with a borrow, because you're borrowing from the next digit, the more significant digit. So once again, you only have 4 entries to remember, 3 of which are completely obvious. Only one is kind of like, okay, I guess I have to remember that one. I can sell that to elementary school kids.
But they can't vote.
They cannot vote, but they can ask their parents to vote. I can hold their kids hostage. That's the strategy in schools these days. Yep. There was a hand somewhere.
Oh, I was just going to point out the voting process.
Oh, yeah, it's okay. I can influence the kid, and kids can tell their parents, my teacher told me to vote blah, 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 or else, my grade is going to suffer. All right, Okay. What is the only downside of binary numbers? There will be more digits, okay? In other words, if you want to express a value that is close to 4 billion, you will need 32 binary digits. In base 10, you will need what? 11 digits? No, 10 digits. 4 followed by 9 zeros is 4 billion, okay? That's the only thing that is inconvenient with binary numbers, okay? So in this class, we're not going to focus on binary numbers and all the other bases, but this is something that you have to understand eventually, because if you're going into computer science, into math or engineering, you will have to deal with different bases of numbers. Okay. So we'll stop here today, and then we'll continue the discussion of nested loops or nested statements on Thursday. So read ahead of me a little bit.